All right, go have your textbooks out if you would. Please open to page 171. You had just a couple of questions to answer and then one problem to work as well. Page 171, questions 17 and 18. You also had problem number 9. Questions 17, 18, and problem numero 9. Is that right? 9? Yeah. All right, question number 17. What is the input force for an inclined plane without friction? And then what's input force for an inclined plane with friction? Michael?
The input force for an inclined plane without friction is equal and opposite to the load's weight. With friction, it is equal and opposite to the load's weight in addition to kinetic friction.
Good, but I would add one little caveat to the weight. Did you have something slightly edited? The weight in the X, the component of weight that is in the X specifically. All right, good. Number 18, what is the IMA of a screw, and identify each variable? We're actually not going to get to that today. We'll get to it later, but Audrey?
The IMA of a screw is equal to 2 pi r over p, where 2 pi r stands for the circumference of a circle over the pitch.
Good, and the circumference of the circle is not necessarily the circumference of the screw, but the handle or whatever is on the screw jack, and we'll get to that, like I say, in probably the next lesson. Let's go and review some things we started talking about yesterday. We started talking about machines, and I said in general, what is a machine, Michael?
An object that makes work easier.
Good, some device, some object that's intended to make work easier. Does it make work happen, class? No, it just makes the work easier. There were 6 simple machines, and let's see, Audrey, without looking over at the poster, because I hid it in the back now. I don't think Kendall could really see it anyway. I looked at the video yesterday. Yeah, you pretty much couldn't read anything. Poster's too small. But can you remember how many of the 6 simple machines?
A lever, inclined plane, screw, pulley, wheel and axle.
Michael, the last one?
Wedge.
Wait, still, hey, not bad. Got 5 out of 6. Very good. Let's see. We talked specifically about the lever yesterday, and I said for our purposes, for the math to work, we have to assume that a lever class is, yeah, that's not too much of a terrible stretch, but inflexible. We have to assume the lever's inflexible, or you've really got no math to go off of at all. And really, truly, if you're using something as a lever, you're not expecting it to spontaneously bend. Like, you sit on the seesaw and you're like, okay, that's a problem. Okay, no, the seesaw doesn't really bend under your weight. Minimal, right? Minimal shearing force there, but you're not really expecting too much bending there. Here we said with a lever, the key to a lever is that it must be able to pivot, right? Now, what do we call the pivot point of a lever? And the pivot point here is called the fulcrum, and fulcrum, there we go. And we said that on this lever, the fulcrum is kind of the dividing point, if you will, this pivot point. And then on one side, you're going to put force in. On the other side, force is going to be put out. The distance from the fulcrum to where the force is put in, that there is referred to, class, as?
Lever arm.
The lever arm. There we go. I got the word arm from Audrey. And specifically, if it's where the force goes in, we call it the input lever arm. Do you remember how we represented the input lever arm's length? Well, that would actually be like how far down you push it. That would be the D sub I. But the length of the lever arm, we represent with the letter R, R sub I. R for radius, because in a sense, if you imagine spinning it all the way around the pivot, it would make a circle be the radius of the circle. And then from the pivot point, or the fulcrum, to where the force goes out, we would call that, class, the?
R sub O.
R, it's represented R sub O. We call it the?
Output lever.
Output lever arm. Now, the object that is at the end of the output lever arm, the object we are intending to move, whether a deck board, a rock. I remember my dad at one point, we lived in Florida, hurricanes come through, and we had a shed that sat on cinder blocks. Have you seen those? The just metal, cheap metal shed with wooden floor, sits on cinder blocks, and then there's these anchor thingies that are supposed to strap down to the ground. That do nothing. All right. And so it didn't do anything. And so the wind pushed the shed off the cinder blocks, and it fell down next to the cinder blocks. Bad day. So we had to find a way to get the shed up off the ground and onto the cinder blocks. So 2x4, jam it down to the ground, and when you start to push forward, it also lifts up, right? And so the object that's intended to move, whether it's a shed, whether it's trying to lift your car, whether it's a kid on a seesaw, whatever, the object that's intended to move, class we call the load. And then there's another name for the input force. And do we remember what the other name is?
Effort.
The effort. I will generally just call it the input force and the output force, but we need to know that the load is the object specifically that is receiving the output force. We then talked yesterday about some equations that had to do with the lever. One of them was called the law of levers. I believe you used this in your law of levers, and I believe you used this in the homework problem, which we'll get to in just a moment. What was that law of levers equation, Michael?
F5 times R equals S sub O times R sub O.
Good. And if you're watching on YouTube and you're like, I think that's torque. It is torque. We're going to talk about torque in a couple of chapters. But yeah, the law of levers, the force of input force times the length of the input lever arm will equal the output force times the length of the output lever arm. There was another equation that I wanted you to know, though. It was 3 ratios all equal to each other. And it's where we got this from. Do you remember the 3 ratio equation by any chance, Audrey?
Is it F sub I over?
Other way around, F sub O over F sub I. Not so much. Michael, what?
D sub I over D sub O. Oh.
All right, so make sure this is in your notes. Double check your notes. Make sure you got this down. And this is the first thing I had you write down for levers. And this is actually where we got the law of levers from, was from the first and last ratios in this. I kind of ignored the D sub I. We did say, obviously, that you have to push the lever down further on the long end than it will push up on the short end. That's okay, because the greater the difference in distance, assuming inflexibility, the greater the output of force that you're going to get. So we have these 3 ratios. And the reason it's important to know the 3 ratios is that this first ratio tells you how much the machine, the lever, has multiplied your force. In general, what term, 2 words, what term describes the ability of a machine to multiply force? Audrey?
Mechanical advantage.
Good, mechanical advantage. Mechanical, of course, referring to machine, and advantage meaning you are helped by using it. All right, so the idea of the machine was to make work easier. It does that by putting out force you could not put out yourself. Mechanical advantage, and this ratio of forces literally, actually tells you how much it multiplied your force. The ratio of output force to input force. So we call this ratio, output force to input force, class, we call it the...
No.
It actually shows you how much it multiplied your force. Actual mechanical advantage. It actually shows how much your force was multiplied. Now, for our purposes, we said these other ratios will have to be equal because we have to assume no flexion. We have to assume friction doesn't cause any problems along the way. In reality, there is just the tiniest bit of flexion, or at least if there's more than a tiny bit, it's not working very well. But there will always be at least a minute degree of flexion, and there will be some friction, certainly. And so these ratios won't always exactly equal, but we're assuming they would. This is based on the design of the lever. These ratios here tell you what should happen for the force. Now, usually output force is not quite as good as we think it should be because of those minor factors. Again, for our purposes, we're assuming an ideal world, it'll work out great. But these 2 here refer to the design of the lever, based on the lengths of the lever arms, based on the distances that the lever arms have to move at the ends in order to operate. So these are based on design, and they tell you what should happen, how much force should be multiplied. So either of these ratios, technically this one, but of course that works as well for a lever, this ratio gives us class the IMA, which stands for ideal mechanical advantage. Now, in either case, whether it's force over force, distance over distance, or even radius over radius, lever arm over lever arm, what's going to happen to the units in every case? Gonna cancel. So AMA and IMA, or mechanical advantage measurements, are unitless values. Let's take a look at the homework problem that you had. Page 171, number 9. It did not ask about mechanical advantage, though we can approach that in a moment. Go ahead and read number 9 for us. They're on page 171. Michael.
A farmer is prying a stump with a 1.6 meter iron rod. The rod rests on a rock 0.3 meters from the lower end. If the farmer can exert a downward force of 180 pounds on the upper end of the rod, how much upward force does the rod exert on the stump?
All right, so we have ground, we have stump, and we have rod, and we have rock, okay? So farmer has rod, he jams it into the base of the tree trunk as best he can, puts a rock under one end, and he pushes down. As he pushes down, other end has to push up, right? It says he pushes down with a force of 180 pounds. We would call that the effort or the input force. 180 loads of input force. If he's my size, that's pretty much all of his weight. He's putting all his weight into this thing. And it says how much force is lifting up on that tree stump. What is the output force on the load? Now, it tells us that the rod rests on a rock that is 0.3 meters. So this distance from rock to tree stump is 0.3 meters. We would call that length from rock, which is my pivot, which is my fulcrum. We call the distance from the fulcrum to the end where it gets to the tree stump. We call that the output lever arm, represented R sub O. The other number they give us is 1.6 meters, but that isn't the input lever arm. What's the 1.6 meters? That's the total length. The whole thing is 1.6 meters. So what is the input lever arm? 1.3 meters is the R sub I. We'll use the law of levers equation. I trust you did this. You'll take the 180 pounds. It did pounds and meters in the same problem. Weird. All right, 180 pounds times 0.3 meters, excuse me, 1.3 meters equals whatever the output force is times the 0.3 meters. Did you have this in the homework last night? Michael says yes. Audrey, did you have the 1.6 for the R sub I? Yeah. Okay, it makes sense now. They tricked you. They were being mean like that. And the meters cancel anyway. I don't know why I bothered writing it that time and not the other time. Obviously, the lobes here means our answer will come out in lobes. And multiply the 180 times the 1.3. We divide it with 0.3. How much force is lifting up on the tree stump, Audrey?
780 pounds.
780 pounds of force lifting up. Now, that's if there's absolutely no bending, the rock doesn't shift a little bit, the rock doesn't push down into the ground at all. That's perfect world scenario, right? But we have to assume that. If indeed you get out 780 pounds and you only put in 180 pounds, you didn't ask this, but at your seats, find it now. What is the actual mechanical advantage? Call it when you got it. 4.33333 rounded to two sig figs. 4.3, meaning if indeed it really put out 780 pounds, it's multiplying his force by 4.3 or 4 1/3. All right? If we want to find the ideal mechanical advantage, technically you take the distance he pushes down times the distance it lifts up. Now in reality, what probably happens, unless you really got down and cut off some of these roots, right, to where the tree stump is not being held in place by roots, only by friction with the ground, then probably he barely pushes down at all, and it barely pushes up at all, and he gets frustrated, and he goes and gets some dynamite and blows it up. All right? That's not necessarily the best move. Or you bore a deep hole down in there, pour some gasoline like that on fire, let it burn from the inside. That's great fun, too. I'm not recommending any of these things for the record, just, thoughts that pass through my mind as I think of how about, or you can pay a stump grinding service instead of trying to gouge it up, but whatever. Probably in reality, there's not much distance down or distance up. But, yes?
Isn't gasoline combustible, so it'll probably explode?
Well, I mean, it would burn, right? Combustible means it burns, not explodes necessarily. If you wanted to explode, you need a dynamite, right? So you drill a hole, stick the dynamite stick down in there, light the fuse and run, and Anyway, you remember Dr. David Gibbs Jr. came to homecoming last year for the big 75th anniversary homecoming. Well, I was listening to some of his stories on YouTube, and he tells a story about some bees that he had on a farm, and they'd fly out of the hole every morning, and then they'd fly back down into the hole at night. I don't know what kind of bees these were, ground bees of some kind. He's like, what do I do about the ground bees? Well, a friend told him to pour some gasoline down and then light the match. Well, the friend didn't tell him how much gasoline to pour. So he just figured I'd pour until it fills the hole up. Well, that hole apparently was real deep. Like, it was quite the colony down there. He ended up going through like 5 gallons of gasoline. Well, of course, you know that gasoline, as you pour it, the liquid goes down, but there's also vapor, which is also combustible. And by the time he was done pouring 5 gallons of gasoline down in the hole, so anyway, he singed eyebrows off, and it was a bad day all around. But anyway, so I'm not recommending you do that sort of thing. Anyway, how do we get off on that? IMA, yes, IMA, supposedly is the distance down, distance up. The easier way to find it for a lever would be to compare the input lever arm to output lever arm. So, if we compare 1.3 to 0.3, what do we get? Big shocker? The exact same thing, because IMA says this isn't a perfect world. What would happen? We made a perfect world, so of course the AMA matches. Realistically, it's probably a slightly lower number than 780 pounds, so probably the AMA comes out to a smaller value, where the IMA is the ideal, this is what should happen. But with levers, we kind of created a perfect world, where AMA and IMA will have to be equal to each other. All right, questions on this? Questions on levers? Now, I mentioned yesterday there are 3 different classes of levers. Let's put this in your notes now. 3 different classes of levers, ways in which you can design a lever based on what you want. First class of lever is the most basic lever, the one that I keep drawing in the picture, the one that we had in the problem last night, the one that just feels like a lever, right? And that's class 1 lever. A class 1 lever has the fulcrum in the middle between the output and the input. The key to each class is what is in the middle. The fulcrum has to be in between for a class 1 lever. For each of these, I'm going to give you an example that I think will be an easy one to remember, and I think the seesaw is perhaps the easiest picturable example of a class 1 lever. Just picture a seesaw. Now, with a class 1 lever, you can do a couple of different things. One way you can use a class 1 lever is to multiply force if input force is applied to the long lever arm. I'm just going to say applied to the long side. A class 1 lever will multiply your force if the force is applied, or the input force. Sorry, Kendall. Ha, there we go. All right, now it's not blocking your view. Now it's blocking Michael's view. Like, yeah, no, he's good. Everybody's good. Camera's good. Audrey's good. Michael's good. Kendall's now good. All right. If the force is applied to the long side, for instance, in the case of the farmer and the tree stump, right? He put his force on the longer side of the what you call the pry bar thing, right? So that multiplied his force. However, a class 1 lever can also multiply speed if the input force is applied to the short side. If the input force is applied to the short side. For instance, let's take a trebuchet, right? A catapult, right? Now, the idea is you want the arm to whip really fast to launch the rock. So they use a great deal of force and cables and winches and stuff. But the point is that when they cut the rope, you've got a ton of force that's applied to the short end of the trebuchet. The longer arm that holds the rock whips a lot faster. So you got the little piece moves like this, and the big piece moves like that, and you multiply speed. Another example of this could be, for instance, in rowing, right? You've got the oarlocks on the side. The guys in crew, I think is what it's called, have the paddles that stick way out there, and they're pulling on the short side. By pulling on the short side, they make the other end of the paddle move very, very quickly. Now, you have to put in a great deal of force for this. These guys are incredibly strong in their upper body strength, but you get a lot of speed out of the end of the paddle. Now, when normal people like me go canoeing, I don't do it that way. Okay, I'm holding way down here as I paddle, and so I got the long end, so I'm still multiplying force because I'm not in a race. But when you're in a race, you want to multiply speed. Okay, so either one can be accomplished by a class 1 lever. It makes it unique. The other two classes of levers can only multiply one or the other, but not both. Because only the class 1 lever do you have options on which of these two sides is longer. The class 2 lever. The class 2 lever has the output or load in the middle. The fulcrum will be at one end and the input at the other. So because the output or the load is in the middle, the output lever arm must be shorter than the input lever arm. It has to be. And if the output's shorter, you're always going to multiply force. So a class 2 lever always multiplies force. A great example of this for you to jot down is the wheelbarrow. Because it's easy to picture. Where does a wheelbarrow pivot? At the wheel. In the middle, you have the load, literally. And then you grab the handles on the outside and you lift. And as you lift the handle, say 6 inches, the load lifts off the ground, say 3 inches. Well, that's all you need. You just need it not to drag along the ground as you roll it along. And you don't have to lift nearly as much as whatever's in the wheelbarrow weighs. So a wheelbarrow, a great example of a class 2 lever. A class 3 lever puts the input in the middle and the output or the load at the opposite end from the fulcrum. Well, again, think about what's going to happen then. The input lever arm must then be shorter than the output, which means a class 3 lever always multiplies speed. That's all it can multiply. A good example here is a baseball bat. Again, assuming you're swinging it like a baseball bat, okay? Where is the pivot? I know the whole body turns, the whole arms move and everything, but when you actually finish the swing of a baseball bat, where's the pivot take place? The wrist, the extension, right? You swing the baseball bat, your whole body rotates, but at the end is that swing, right at the end. Well, what happens is your hands are actually applying the input force right next to the wrists. So the input lever arm is incredibly small. The output lever arm is greater depending on where the ball contacts the bat, usually out toward the end of the barrel, on hopefully what we call the sweet spot. Right, but as you swing, we have the pivot, we have the input force, and then out here we have the end, which means you make a small twist, and the end of the bat makes a much larger swing, which gives you bat speed, which is the key to hitting with power is bat speed anyway. It's not huge muscles, it's how fast can you whip the end of the bat around, and that all comes from the wrists. So we have the wrists as the fulcrum, the hands provide input force just above the wrist, and the output is where it contacts the ball. Fly swatter would be another good example, right? You have the pivot point, input at the end, and that's why you try to smack a fly, you usually miss the fly. You're too slow. But if I do that, I can get the end to whip around faster than the fly can get away. Also, there's little hole passageways for the air to fly through, so that way there's aerodynamic, it doesn't encounter a ton of air resistance, and wham, it kills the fly. And it's great, unless you love flies. If you love flies, I'm sorry. Don't mean to offend anyone here. No flies were actually harmed in the making of this lesson. Questions on this? Your book gives some more examples you can look at there on page, whatever it is. I don't know. Page 165. Got some different examples of the classes of levers and all of that. We'll actually look at some of these a little bit later on. We won't be able to today. Kendall, we are looking at a test coming up on Wednesday. Okay, so that'll be lesson 80 is what we're shooting for. So we're going to do most of our demonstrations of these machines after the test so that we can fit things in as quickly as possible. Questions on levers? I feel like we understand lever pretty well. By the way, the example of my dad's lever, okay, we had the cinder blocks, we had the shed that was supposed to be like this, and it had fallen, it was supported up on other struts as well, and it fell down, so the floor was actually on the blocks instead of the support on the blocks. So what he did was he jammed the lever down, he used the ground as the pivot. He pushed up, and it pushed up. This is input, output, fulcrum. What class would that be?
2.
Class 2, because the output is in the middle, like a wheelbarrow. If you put a block of some kind here, and it pushed up here, now that would make it class 1, right? So anyway, do you want to share that very quickly? All right, let's move on to our next simple machine, and we don't have to spend a lot of time here because the inclined plane is something we have worked with a bunch. We just called it by another name. We called it a ramp. So next section, your notes, inclined plane, and then in parentheses put ramp. We have worked a bunch of ramp problems. We just haven't looked at it from the perspective of work being done or mechanical advantage or the terms of a machine. But really all an inclined plane is just a ramp. What does an inclined plane do? Well, the purpose of a ramp is to roll or slide upward rather than lifting. To roll or slide upward rather than lifting. To roll or slide upward rather than lifting. Think about it. You got a person in a wheelchair, and you come to a wheelchair ramp, you roll them up the ramp. The purpose was to take them from this level to a higher level without you having to lift the wheelchair or, depending on their condition, if they were able to, get out of the wheelchair long enough for you to move the wheelchair up. I don't have experience with that necessarily, but I've had 4 small children. I still have one that's occasionally in a stroller. He doesn't go in a stroller much. He's almost 2. But around here, we've got a lot of stairs. And so when baby boy needs to go up the stairs, either mama picks up baby boy and I'll carry the stroller or vice versa. Or if it's just the 3 stairs, down near the office area, I'll just pick up the boy in the stroller and set him up. But a ramp would be nice, wouldn't it? What it does is all I do is push, and the ramp literally does all the lifting, right? It lifts, I push. That's the purpose of an inclined plane or a ramp. Think about this for a moment. We have our ramp or our inclined plane, because that sounds more technical, right? There's going to be some angle, of course, at which it rises, and you're going to have the object, whatever it is. The applied force is not a lifting force. The applied force is merely a push. What forces resist the push up the ramp? Usually there will be some degree of frictional force that will resist the upward pushing on the object. What other force? Always weight. Now weight technically acts straight down, but remember we said there's 2 components of weight. Specifically, the component of weight in the X downward has to be countered. And you say, couldn't we push something down a ramp as well? Yes, but in that sense, we're not looking at it as a machine, are we? Because which is easier, to push something down a ramp or to simply drop it off the edge? From a work perspective, now, it probably breaks, okay? For instance, the boxes and stuff that we were, not you, that we were carrying, poor Audrey, the boxes and stuff we were carrying downstairs and stuff. Wouldn't it have been easier to just be like, all right, bombs away, but all the cans bust open, it makes a huge mess. So we carry them down, but we're having to exert a force upward, aren't we? If you slide something down a ramp, you're actually doing negative work because the resistance it would be easier just to drop it, right? Greater energy that way. So we're only ever going to look at the inclined plane as an upward movement. That's how it's functioning as a machine. Now again, is there a purpose to, yes, a downward motion? Absolutely. You'd rather not drop the person off the edge. You'd rather roll them down the ramp. We get that, okay? But technically, from a work perspective, it's doing work for you when you're going up because it's lifting for you. We need to know this then. The applied force will equal weight in the X plus the force of kinetic friction. Applied force will equal these if acceleration is 0, meaning constant speed. Now, we've worked these a bunch, so I don't need to rehash all of it, but we know if there's not that acceleration, we have to add a little bit to the applied force to make it win, blah, blah, blah. But generally speaking, when you're using it as a machine, right, when you're using it to lift something, very rarely are you racing up the hill and trying to accelerate as you go. Usually you're just trying to keep a nice steady pace. So we're usually, in this section, going to assume a constant speed going up the ramp. Now, what about the AMA? AMA is always defined as output force over input force. It's true of the lever, it's true of all the simple machines. But think about it. What force does a ramp put out? What does the ramp do? It lifts. If you did not have the ramp, what force would you have to apply? Whatever the weight is. The output force of an inclined plane ramp is the force of weight. because that's what the ramp does. It literally lifts the weight, not the weight in the Y either. The actual weight is what the ramp lifts. What force do you put in? Well, we call it the applied force. This isn't a new formula for AMA. I'm just explaining what the output and input is for AMA. So do write this down in your notes, but we can still memorize AMA is always output force over input force, always. It's just we can define the output and input as weight and applied force specifically for a ramp. Make sense? Now let's think about the IMA of a ramp. Remember, IMA is a ratio based on the design of the machine. In the case of the lever, we said the contrasting lengths of lever arms would make a difference because they contrast the distances that have to be moved, right? IMA is always a ratio of distances that are accomplished. In the case of the levers, we can use the lever arms as an equal representation. But let's think about a ramp for a moment. We've got a ramp. We come to the ramp with a wheelchair, and we get to the end of the ramp, and here's the next level. So here's level 1 down here, here's level 2 up here, the ramp goes in between. What distance do we have to put in to go from this level to that level? With a wheelchair, where do we have to go from one level to the next? The ramp. However long the ramp is how far we have to go, correct? That's the input distance. What is the output distance? What distance does the ramp put out for us? Well, the ramp lifts, right? It lifts. It takes it from this level to that level. This change in height is the output distance. Now notice, the greater the length in relation to change in height, the greater mechanical advantage you're going to get. So a longer ramp is easier to navigate. Now, you two have been here a long time. You guys remember Hodges Hall? Do you remember before the awnings? You'd have been really little back then. But you remember before the awnings. You were like Chloe's age, okay? You also remember before Pastor Rands came, the ramp. That if you tried to actually take it in a wheelchair, you would fly and crash into the auditorium wall or door if it happened to be open. It was almost lined up. You'd like hit the open, it would be bad, very bad. So one thing he did, of course, was he had them pound out the concrete and extend the ramp longer. Now, don't think going down, think going up. Can you imagine a person in a wheelchair trying to wheel themselves up that ramp? But by making it longer, he was able to decrease the angle. And it made it easier for a person if they were propelling their own wheelchair, let's say they would push like this, to go up the ramp, they could actually do it. Also, if you were wheeling someone else, really with safety for coming down. But from a work perspective, it's easier to go up a ramp that's not as steep. Even running, right? You run, I don't know if you run, but if you're running, a hill that's steep is harder to run. A shallower slope, okay, still not favorite, but it's still not that bad, right? So the key is the longer it is, the greater mechanical advantage. Now, I keep mentioning slope and angle and stuff, right? Because the angle is tied to both of these things, isn't it? The angle that we're used to getting in ramp problems is connected to the change in height and the length, because relative to the angle, change in height class is the opposite. And the length is the hypotenuse. What trig function relates those? Sine. But sine would be opposite over hypotenuse. The IMA is the inverse of that. It's the reciprocal of that. You guys know this. We would call that the cosecant. But that doesn't really help because we don't have a cosecant button anyway. So Kendall, it's not the sine, it's the reciprocal of the sine. And we have two ways to calculate the IMA. Either length over change in height, which literally is input distance over output distance, or if you're given the angle of the ramp, take the sine of theta, sine of the angle, and then take the reciprocal. And that'll give you the IMA of the ramp as well. Let's take a look now at example 11.5. They're on page 166. And go and read the problem for us there at the bottom of page 166. Audrey?
A 3,750-pound safe must be raised to the top of a 6-foot platform. A winch is available that is rated at 1,200 pounds maximum. A, if the safe can be rolled on steel rollers of negligible friction, what length ramp must be supplied to lift the safe? B, if the safe slips off the rollers halfway up the ramp, what force will be required to slide it up the rest of the way, assuming the coefficient of friction is 0.25?
All right, so they got a little picture for you there. It's just dawned on me, if I roll that all the way over there, then it's not in the way of the camera. I don't know why it took me so long to think of that. Also, I get to look at it and enjoy it now too. Anyway, all right, so they give us the picture. The ramp needs to go up a total height of 6 feet. That's the change in height that needs to be accomplished, correct? Now, if there was no ramp, literally, what would you have to do to get it up there? Pick it up and lift it. Or, you know, like the winch, right? You have the winch and try to pull it straight up. But is that going to work too good? No. Because it weighs how much?
3,750 pounds.
And the winch is only rated at?
Yeah.
Yeah, it's not lifting that thing. You would need 3 such, actually you need more than 3 such winches to be able to lift the safe up. But by putting it on a ramp, the ramp actually does all the lifting. The winch just pulls horizontally, correct? So as we look at the picture, we've got, that's the safe, and it's on rollers. And it says the rollers are of negligible friction, well lubricated, they just roll really nicely. Well, remember, we said applied force has to equal weight in the x plus the force of friction. But if there's negligible friction, then you realize the applied force only has to match the weight in the x, correct? Well, the applied force, the force of the winch as it pulls it up the ramp, is rated at what maximum force?
1,200 pounds.
That's all it can put out. That is the applied force, which means the weight in the x, right here, that weight in the x can't be any more than 1,200 pounds. So technically, we already know what the weight in the x has to be. The question is, how should we design this ramp? How long should we make the ramp so that the weight in the x comes out to the 1,200 pounds that we want? Does that make sense? Now watch, I'm going to zoom in just a little bit here. This is the weight. This is weight in the x. It's 1,200 pounds. The actual weight is 3,750 pounds, correct? Question is, how long should the ramp be? And we know that the length of the ramp and the change in height are connected because this is input distance, output distance, class. That's the IMA. IMA is length over change in height, but IMA is also
The 1 over sine.
and therefore, length over change in height equals 1 over sine theta. Does that make sense? Here's the deal. I can find the theta based on the weight in the x and the weight, the true weight. What trig function relates these two things?
Tangent. Or no?
Sine. This is the opposite. This is the hypotenuse. I know that the sine of theta equals opposite 1,200 over hypotenuse 3,750. So if I just divide these numbers, I'll get the sine of theta. What does the sine of theta come out to? It's a weird little decimal, that's fine.
0.32.
0.32? Is it coming exactly to 0.32? Oh, hey, that's awesome. All right, I like that. I was like, I could see it working out evenly because they're divisible. There are multiples of 5 in there. You knock off some zeros. So the sine of theta comes to 0.32. What that means is that the length, whatever it is, that's the question, over the change in height, 6 feet, must equal 1 over the sine of theta, which we said is 0.32. How do we solve? Cross multiply. We'll take the 0.32L equals 6, and if we divide the 0.32 from both sides, we'll get the length of the ramp that we need.
18.75.
Just making sure, yes, what length ramp? So you said 18.75 feet. Rounded, sig figs, 19 feet. because it may not work out perfectly exactly. So we'll say we need a 19-foot ramp to make this work. So as long as we have 19 feet worth of boards, strong boards, that can hold this and don't bend under the weight, right? Assuming we got a nice sturdy ramp, reinforced well, 19-foot ramp, my winch works great. And then, tragedy, sadness, vexation of spirit. It falls off the rollers. And now it's just sitting on the ramp. Well, in order to put the ramp back on the safe back on the rollers, we got to pick that safe up. We already did that once to get it on those rollers. I don't want to pick it up again, especially not when it's on a slope. I mean, the rollers are now rolling down the ramp and the safe is just sitting there, right? So now there's no rollers. Now all of a sudden there is some friction force, isn't there, that has to be compensated for. There's the question. How would I find, again, friction's going to act down the ramp now. How do I find friction force? Normal times coefficient, right? Okay, how do I find the normal force? In the y. Oh, well, I need to know the weight in the y then, don't I? Two ways you could go about it. One way, hark back, Kendall, to your geometry days. If you know two sides of a right triangle and you want to find the third side, class, we would use the Pythagorean theorem. Or if the sine of theta is 0.32, take the arc sine of 0.32, I can find the actual angle itself. Go ahead and do that real quick. What is the actual angle that the ramp is going to make?
18.6.
Put this in the memory of your calculator, because for Kendall's sake, this is a more repeatable process. We could find the angle. And then, if I want the weight in the y, and I know the weight, what trig function relates to these two? Cosine. I know the cosine of the memory value 18.66 blah 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 degree angle equals the opposite or adjacent weight in the y over the hypotenuse 3750 lobes. Can we just cross multiply? And how much weight in the y is there?
3,555.52.8157.
Blah, blah, blah. Put that in memory too. Did you get the same thing? Take the cosine of the memory value, cosine of 18.66, blah, blah, blah. Multiply that by 3750.
Okay.
Got it now? Now, again, we could have used Pythagorean theorem. So now that that's in the memory anyway, 1200 squared, or excuse me, start with the hypotenuse squared, 3750 squared, minus 1200 squared. And then take the square root of that answer. Should still get 3,552.81. So either way technically works. That's the weight in the y. If that's the weight in the y class, that must also be the normal force. Weight in the y downward, countered by normal force upward, and if that's the normal force, 3,552.81, multiply that by the 0.25 coefficient of friction, memory 2 times 0.25, how much friction force is there?
800.203.
All right, so we have weight in the x, 1,200 pounds. Applied force was 1,200 pounds. They countered each other. It was rolling at a nice steady speed. But it's off the rollers now. There's an additional 888.2 pounds of force needed. And the question says, what force will be required to slide it up the rest of the way? Well, the guys are going to have to get behind and just push. Total between the however many guys are there are going to have to push with a force of 888 pounds, basically. That's okay. It's still better than lifting 3,750, but they're going to have to push with that much combined force. But it was asked how much force is needed. Well, I need, the winch, of course, is still doing 1,200 of it, but how much total force is that going to have to be?
2,088.20.
Good. And round it off, I think it was 2 sig figs, 2,100 pounds total. Again, the winch is still providing the 1,200 of them, so it's only an extra 888, but total of just over a ton of force required. Do we see how we can use things like the AMA and stuff like that, IMA? Now, let's think about this. 2,100 pounds of applied force needed, right? And it weighs 3,750 pounds. So what's the AMA? If it puts out 3,750, now granted, that was wind jam people, and it only required a total of 2,088.2. What's the actual mechanical advantage of the ramp?
1.79.
Oh, so about 1.8 basically would have been the AMA of the ramp after it fell off the rollers. Now before it fell off the rollers, weight was 3,750. We were only using a 1,200 pound winch. What was the AMA before it fell off the rollers? 3.125. If I wanted to find the IMA, we said we take the length over the change in height. The length was 18.75. The height was 6. What was the IMA? 3.125. Again, when we create the perfect world, there's no friction. AMA and IMA are going to be equal, ideal and actual. But when we go to the real world, okay, there's not frictionless. That's where the AMA begins to take a little bit of a hit. All right, questions on the inclined plane? All right, we'll work more with that in the days ahead. No homework this evening. Again, don't forget we have a test coming up a week from today, lesson 80. And we'll do more work with some of the machines, actually playing around with some of these machines in class, in the lab, after the test. Only because that's the way it works sometimes. All right, you are dismissed.